Well, we found some interesting results in the last section, 7.1 on momentum, and we're able to define momentum. Here in section 7.2, we're going to look at collisions between two particles. The collisions that we're going to start worrying about are called totally inelastic collisions. And momentum is conserved for these, but energy is not conserved. Well, let me give you an example of what these types of collisions are. These are collisions where objects actually stick together after the collision, and we have the maximum possible loss of kinetic energy consistent with the conservation of momentum. In fact, we'll show that in one reference frame, all kinetic energy is lost. Well, let's take an example of what such a collision might be, and we're going to look at that. When two objects come together, these might be two pieces of clay or something like that. Let's say this is mass m1 and it's moving with velocity v1. And here's mass m2 and it's moving with velocity v2. Now I'm going to make this mass go faster so it can catch up with and hit this mass. These could be two cars going down the expressway to our horror, or it could be two pieces of putty, but we want these two objects to stick together. So this is what we'd call before the collision. Then they collide, and after the collision, they're stuck together. You'll notice here that we have one object of mass m1 plus m2, and it's traveling with just a velocity of v. Now, what does conservation of momentum say? It would say that if there are no external forces, and I have no external forces on this system, this is all occurring on ice or in the outer space, and so we don't have any external forces. So we know the momentum before totally is the same as the momentum afterwards by the theorem that we just proved last time. So the momentum is going to be m1 v1 plus m2 v2 must be equal to m1 plus m2 times v. Well, if I tell you what these masses and velocities are, then we can calculate what the velocity is of the final object. Again, you could think of these as two cars that collide and tangle up with each other and slide down the road on the ice. We could think of these as two pieces of putty, but I'd rather think of this as a football player where another player is tackling them. And it's on a perfectly slick surface. So he grabs the guy, comes up behind him, tackles him, and of course the two slide off with some velocity. How do we find that velocity? We solve this equation for the velocity, and so we get v is equal to m1 v1 plus m2 v2 divided by m1 plus m2. And this is a standard test question. Compute the velocity of the two players after the collision, or the two cars, or the two pieces of putty. And again, this is called a totally inelastic collision. And we could actually put these, put some numbers in here. We could have two football players. Let's make one of them 100 kilograms. We'll make this guy 100 kilograms. 100 kilograms. And he's going to be going with a velocity of 8. And here's another guy. He's 90 kilograms. And he's going faster. He's going with a velocity of 10. You'll notice they're both going in the same direction. And so what would this equal to? It'll equal to the first mass, 90, plus the other mass of 100 times v. So this would be 900 plus 800 is equal to 190 times the velocity, or the velocity would equal to 900 plus 800, which would be 1,700 divided by 190. I'll let you use your calculator to figure that out, what the velocity is, and that would come out in meters per second. It's a standard type of equation, and you'll notice we have one equation in one unknown. The unknown is the velocity. We don't know what the velocity is after the collision. Now, a question that's also sometimes asked is how much energy is lost in this collision? Well, what happens to the energy is that when these two things hit with each other and stick together, that causes the molecules to bounce around randomly inside the putty or inside the two football players or the cars, and they heat up. And that heating, as a result of the collision, takes away kinetic energy for the motion as a whole. And we can compute how much energy is lost by looking at the energy before, 1/2 m1 v1 squared plus 1/2 m2 v2 squared. That's the energy before. And the energy afterwards is going to be less. This is E before. And I'm going to subtract E afterwards and look at what energy is lost to heat. The answer would be, there's the total energy before. I'm going to subtract 1/2 of m1 plus m2, that's the total mass here, times the velocity final squared. And this equation right here will give us the total energy that's lost to heat. Now let's look at one example of that. In fact, what I'll do is I'll tell you that in a moment we'll compute what is called the center of mass. And if we compute that center of mass, you notice the center of mass is moving. This object's moving and this one is too. So as that center of mass moves along, if I were to run along with these two particles at the velocity of the center of mass, then in fact, what I would see is this mass going this way and this mass coming toward it. I would be in a reference frame where the two masses would approach each other, hit, and stand still afterwards. In other words, the velocity after the collision would be 0 in that frame of reference. What frame of reference is that? It's called the zero momentum frame. m1 v1 plus m2 v2 is going to be equal to 0. And that's going to occur only when I subtract the velocity v from each of these. Then you can see that if that were done, that I'd have a total momentum of 0 before and after the collision. A simple way to see it is imagine those two masses, m1 going this way and m2 going this way, and they're going with velocities v1 and v2 such that with their masses, this momentum is equal and opposite to this one. Therefore, when they hit, pow, they stick together. They don't bounce off. And that's it. They just stick there. And therefore, the velocity afterward is 0. In that frame of reference, you'll see that you've lost all of your kinetic energy. And that's where you can, of course, the loss of kinetic energy is different in different frames of reference. But here, in this frame of reference we originally had, we took the original kinetic energies, subtracted the final kinetic energy, and looked at the loss. E before minus E afterwards is E lost to heat. So on the problem, somebody may ask you how much energy was lost to heat. The way you'd work that is plug in these numbers right here into the energy formula, then take the velocity you compute here, square it, multiply it by 1/2 m1 plus m2, subtract that from the previous energy, and you would have the energy loss of the system. Now, one place where this is really neat to look at is the concept of what's called the ballistic pendulum. Again, I'm continuing on 7.2, and we're going to look at a ballistic pendulum. Ballistic pendulum is a string that hangs down with a block of wood or some other absorbing object. This will be anchored on the ceiling. And what we're going to do is take a gun and fire that gun so that a bullet comes out and it sticks in this wood. Now, what is our objective? Our objective is to find out what the muzzle velocity of this is. We want to know how fast that bullet is coming out. Well, that's kind of a hard thing to do. But watch us as we do this. Let's assume that this object has a mass capital M and a bullet has a mass small m. The velocity of the small bullet is a velocity v as it moves along, and the velocity of the mass after the bullet gets stuck in it, there's a bullet stuck in the mass, this is going to swing in the upward direction. And it's going to go to some height. How do we know? Well, what we can do is we can put little lightweight objects here, and as this pendulum swings over, it'll knock all these objects down until it gets to one that is just the object that would be on the other side of where it would stop. So if these were like little matchsticks or something like that, toothpicks or something, it would knock these down, so we can say, oh, it stopped right here. Then we would know what the height was of the system, and we know that the energy afterwards would be mgh, and so we can look and see what the velocity was down here. How can we compute that? Okay, when we look at this bullet coming over here and embedding itself, we have initial velocity. This is initial. We have a small mass m and a bullet with mass m, velocity v, and that's what we have initially. And then finally, what we have is we have a mass m and a bigger block going at a velocity capital V. And we know this is after. That's because this block was not moving initially. So our only momentum is from that first bullet, from the bullet itself. Afterwards, we have the bullet and the block going with a velocity v in this direction. And so we know that they must be equal. Well, how do we calculate this velocity v? Well, we can look at this velocity v because once this bullet embeds here, although we've lost a lot to heat, we've still got, at that point, right after the embedding, this is going to move with a velocity v and give this object kinetic energy. And once the bullet embeds, we've lost everything to heat we're going to lose, and we're going to have a kinetic energy of this block that's going to take it upwards. So we know that 1/2 m plus m v squared, that's the kinetic energy of the block right here, is going to be equal to mgh. And we can compute the height because we know how far it's going to swing. Since we know the mass, I need to put both masses in here, m plus m times gh. Since we know the height, then we can compute the velocity. Knowing the velocity here, we can compute the velocity of the bullet. So how is that done? We can cancel the masses from both sides and conclude that the velocity is twice gh with a square root. This is the large velocity. This is the velocity of the block with the bullet. Okay, there we've got that. Now we're going to take that and stick it in here and solve for the velocity of the bullet. The velocity of the bullet is going to equal to m plus m divided by m. We're going to solve for this small v, velocity of the bullet. And now I have to multiply that by the velocity here, which is times the square root of 2gh. And that tells us what the muzzle velocity of this bullet is. And that is a kind of a neat apparatus for very simply computing this if you don't have time-lapse photography or thousands and thousands of dollars worth of equipment. You can just hang a wooden block down onto fine wires or strings and compute this and see how many things it knocks over and how high it goes. So that's a good application. And I've already done the problem with two football players where one tackles the other, or in an auto crash. So understanding the calculation in the ballistic pendulum is important. You'll notice energy is not conserved in the first process. That's important to separate from the second process. The bullet comes over, hits the block. When it does that, energy is lost to heat. But it still has some energy. At that point, the energy of swinging is conserved. The gravitational energy is conserved. So we have that 1/2 mv squared is equal to mgh. And the masses cancel. And we're able to compute the velocity of the block in terms of the height to which it was able to rise. That does the ballistic pendulum. You should be able to calculate that. And the other example we worked was the two objects that stick together, and we want to calculate their final velocity. We may also want to calculate how much energy was lost in either of these two problems. Energy is always lost in a totally inelastic collision, and you should remember that the maximum energy is lost consistent with the conservation of momentum. Remember that last sentence. Okay, that finishes section 7.2.